Just in case this hasn't been posted, we had a question about a cone, okay, with a spherical top. And there was a bad statement on one of the tests, but this is the way the cone should look. You have a cone from here up to here, and then you have a hemisphere on top. And what's the total volume of this cone? Well, the volume of the conical part is 1/3 the volume of the cylinder that would confine it, 1/3 pi x squared y, okay? Because, of course, a cylinder of radius x, and of course the radius is x and this dimension is y, would have a base area of pi x squared and an altitude of y, giving it this base area times altitude volume, cone, 1/3 of that, okay? And to that we add half the volume of a sphere of radius x, because we have a hemisphere sitting atop of this. So there we have it. Now, that's okay. I just note that in spherical coordinates we could describe this cone easily. That wasn't part of the problem somebody's asking about. It was just, how do you get the area of that, or the volume of that thing? Well, that's how. In spherical coordinates, you could simply say that, well, y goes from 0 to rho. That's a distance from here to here. Rho goes from 0 to y, and actually it doesn't. That's just kind of completely wrong. Rho would go from, looks like I'm on a roll here making errors. Rho would go from 0 to the square root of y squared minus x squared. Y squared plus x squared, because that's the length of this side here, okay? But you don't have a hemisphere with the same radius on top, so yeah, nice idea, but forget it. What I had before would be a cone. We have y here in the arc of a circle, so that all these distances are y. And y does not correspond to vertical coordinate. And that would be a typical cone in spherical coordinates. And I believe we kind of know that. Okay, another question was differential. Okay, you have PV equals nRT, so that n equals PV over RT. R is always constant, it's the gas constant. And we also assume that T is constant. So R and T are both constant. So the things that are varying are P and V, and changes in P and V will drive changes in N. So the differential of N is what? Well, it's factor out the V over RT and end up with a P, and you find that the contribution to the change in N, or the rate of change of N, for given volume and so forth, is V over RT times dP. In other words, then, you're treating P as a variable. You're essentially taking the derivative of N, and you've got a product rule. So you have the derivative of P times V, and then the P times the derivative of V, and the division by RT, since these are constants, just factors out of the whole thing. So, first part of that, when you're doing the derivative with respect to P, you get a dP. Okay? Now, when you do the derivative with respect to V, you get a dV, and of course that's multiplied by the P over RT, which are the coefficients of V. So we treat P as a treat V as a constant, take the derivative with respect to P, except we're not take the derivative of P, except we're not saying what we're taking the derivative with respect to, because it doesn't matter. Okay? And it's kind of like taking a derivative of V holding P constant. We get this. That's our differential. And it follows from the differential that a small change in P and a small change in V give you this approximate change in N. Okay, whatever it is that's driving the change in P and the change in V, this is going to be your change in N, if you have a very small change in P, a very small change in V. And many of you have taken the physics course, so that's going to be very important in a couple of months. So, we then want to show what the percent change or the proportional change is in N as related to the proportional change in P and V. So, if we divide both sides of this thing by PV over RT, then we're dividing by N, right? So we get delta N over N, and then we get delta P times V over RT divided by PV over RT. Well, the V over RT goes away. We end up with delta P over P. And when we do the same thing to our P over RT delta V, dividing it again by PV over RT, we get delta V over V, which tells us that the percent change in N, if this is, if delta N over N is expressed as a percent, then we have a percent change, okay? Same with delta P over P and delta V over V. So we have percent change in N is the percent change in P plus the percent change in V. Very important for percent uncertainties if we're observing a system. And we have small uncertainties in the value of P and V, then we would express the uncertainties as delta P and delta V. And we would find that the percent uncertainty, well, we can express the percent uncertainty in P as delta P over P and delta V over V. The percent uncertainty in V is delta V over V. And when we add those, we get the percent uncertainty in N. Okay? So percent uncertainty in N is percent uncertainty in P plus the percent uncertainty in V. Now, we could easily hold other variables constant. If we held P constant, if we held, let's say, if we held P constant, then we would end up with expressions that require us to use the quotient rule, okay? If we had powers on any of these, well, you have to explore that. So I'm not going to comment further, but that's what we have. Another example was the ball on an incline, where we measure the distance the ball goes down the incline and the time it takes. And then we infer the acceleration. Okay, well, if we're measuring S and T from rest, just to do it, in the simplest case, then the average velocity is this, the acceleration is this. And if you have a delta S and a delta T, you're going to get uncertainty. If delta S and delta T are your uncertainties in S and T, then we get the differential of the acceleration is what? Well, quotient rule. It's 2 over T squared times ds, okay? And then quotient rule, you got a 1 over T squared. So it's a minus 2 over T cubed, 2 over T cubed times the 2s times dt, okay? You divide that by the expression for A, you get delta A over A equals delta S over S minus 2 delta T over T, okay? Now, to get the percent uncertainty in A, given a plus or minus percent uncertainty in S and a plus or minus percent in T, you would choose to use the positive uncertainty delta S and the negative uncertainty delta T, so you'd be adding these 2% uncertainties, or add the magnitudes of these 2% uncertainties to get your actual percent uncertainty in the acceleration that you measure. Very important, and if you're in physics, this will be used before the end of the first semester.